especially when it comes to aliens and looking for technosignatures, it's very difficult to get any kind of government funding, especially for that kind of work, because they have to justify the expenses to the public, and maybe some parts of the public think it's not an effective use of financial resources to be doing that. But if we never do it, we'll never know. So there's a trade-off.
The other topic that I wanted to discuss with you, shortest, because I don't want to keep you for too long, is this issue of statites and quasites, or statites and quasites, however you want to pronounce it. So it's another way to essentially hack astronomy and generate these artificial orbits. So what's going on here with these? Maybe if we start with these statites or statites.
Yeah, so that's a good starting point. It's an idea that I think it was Rob Forward, I think is his name. I think he was a science fiction writer that actually patented the idea, kind of remarkably. I didn't patent my ideas. None of the. I can understand why he would do that, but I just don't really care about that. If anyone uses it, it would be amazing to me, and I don't want to put a barrier up to someone using it. So I chose not to pursue that route. But the idea is, if you're in orbit of the sun or any object that's massive, you are in a state of free fall all the time. It's something people don't always realize, but that's why you get this sense of zero gravity. It's not that there's no gravity. It's kind of a wrong label for it, but we're stuck with it. The astronauts in the ISS are feeling gravity. It's just they are constantly accelerating under gravity towards the Earth all the time. And that their horizontal motion, if you like, is just enough to kind of keep them at the same altitude all the time. So they're in a constant state of free fall, which means
the Newton's cannonball sort of idea.
To show how gravity works on Earth and in the skies, Newton designed a thought experiment. He imagined firing a cannon from the top of an extremely tall mountain. From his first law of motion, he knew the cannonball would travel in a straight line at a constant speed forever. But gravity pulls the ball downward. If its speed is low, the cannonball hits the Earth near the mountain. The higher the speed, the farther away the ball lands.
If you throw it faster, it comes farther away. Even faster, farther away. Even faster, it may go 1,000 miles. Even farther, it may actually go almost halfway around the Earth and there hit the Earth.
Newton imagined that if its speed were high enough, the cannonball would travel all the way around the Earth and settle into orbit.
The orbit of the cannonball around the Earth was a balancing act between the cannonball's tendency to fly off in a straight line and its being yanked back towards the center of the Earth continuously by the force of gravity.
Yeah, that's a really good example to sort of understand the concept. And so that means there's a force acting on you all the time, and that force is obviously gravity. What you could do is counter that force. So, when you launch a rocket, that's what you're doing. You're countering the force. Obviously, you can only do that as long as you've got propellant, and that very quickly runs out. What if you could use solar radiation pressure to do this instead? Obviously, we're interested in using radiation pressure as a way of sailing between planets and maybe even between stars. There's lots of ideas about using solar sails for this. Yeah. But rather than trying to go anywhere, you could just try and precisely balance out the sun's gravity. Yeah. And so you just would be hanging there. You wouldn't be in a state of free fall, and there'd be actually no net forces acting on you. You'd just be hanging there. So you would experience a different kind of zero gravity if you're on board that vessel. These things, though, you wouldn't be able to put someone on board it because the material has to be incredibly thin. Solar radiation pressure is very, very weak. So in order to create a significant force, you want a very large area. So it's collecting lots of photons smacking off it.
Which we can tell because we're not being pushed around all the time by the sun, right? We don't go out in the sun and get slammed against the wall. Even though there's a lot of photons hitting you all the time, the force that they apply to you is extremely small. So we need a hell of a lot of these photons hitting a very big surface to get any measurable force.
Exactly. So you'd want, if you took the Earth, then, the Earth, as you say, gets a huge number of photons smacking into it, and that does push us back a tiny bit. But because we are a massive planet, the force of gravity is proportional to the mass of the Earth. In that case, that just completely dominates. So it's nowhere near worthwhile even considering. Yeah. But if you do a really, really thin, light sail, it's so light that actually radiation pressure starts to become important, and you could even balance it on a hairpin almost and just kind of keep it hanging in space. And you can imagine having some kind of active control that it could sort of unfurl and balance itself to adjust for slight modulations in the sun's luminosity, which isn't an exact constant. So this is the statite idea. It's kind of cool.
So you would have something that, instead of orbiting around the sun as a normal planet would essentially just stay in one place while the planets kept going around. Okay.
It's really eerie. Yeah. And like there's modifications where you could, even though you're balancing the sun's gravity, you could sort of keep a very, very wide orbit of the Earth, for instance. So you don't balance out the Earth's gravity, but you balance out the sun's gravity. So you're really, really far from the Earth, and you could do these huge, much wider orbits around the Earth than would be possible using conventional celestial mechanics and gravitation theory. So yeah, it kind of opens up the door to some interesting stuff. And I had this slight tweak of it, really, which is what I called a quasite. So that's where you're not attempting to fully balance out the radiation pressure. That's actually quite a tall order. Yeah. You have to make it it's really at the very limit of what modern materials could do to make something that thin and light. But don't make it so hard on yourself. Just do something that's kind of in between those two extremes. And then it is still falling towards the sun. Because there is a net force of gravity, but that net force is weaker than what it would normally be. Yeah. Another way of thinking about that is that you've effectively made the sun less massive from your perspective. So therefore, through gravitational calculations of like the velocity at which you orbit, that means that your orbit is slower than it would normally be at any given distance from the sun, because the gravitational force is essentially less that's acting on you. So this is kind of cool. You can orbit slow. Have you ever seen, like, a good example for understanding velocities is to, like, you ever seen those things, those coin drops where you put them in and they spin around and they go into the middle and they get faster and faster, right, as they go down. Yeah. And so the same thing happens with planets. Like Mercury is orbiting at the fastest orbital velocity out of any planet in the solar system. And so things speed up as they get closer and closer towards the sun. And that means that, if from our perspective, watching Mercury, it seems to whiz round over and over and over again. But if you made it a quasite and you could change its velocity to whatever you want, you could make its velocity such that its orbital period around the sun is the same as ours. Yeah. Slow it right down. And then you basically have a constant line connecting the quasite, yourself, and the sun. Yeah. That would always just be sort of tracing around. You could put satellites all along this chain if you wanted to, or a whole system of quasites along this chain. And why would you do that? I argue in the video, one advantage would be space weather monitoring. So there's obviously something that, if you ever heard of the Carrington event in, 1859, it was like this giant coronal mass ejection which smashed into the Earth's atmosphere. And it caused a lot of blackouts in the electrical system at the time. And people are worried that would happen again. It could cause, basically, destroy a lot of our modern electronics. And we're obviously much more dependent now than we were back then on our electronics. So there is an interest in being able to predict when these coronal mass ejections would come, so that you could maybe turn everything off and just sort of protect things a little bit, go into protection mode. So
just to explain what's going on there. So you would have this monitoring quasite, for example, or statite near the sun, but it would essentially always be in line and going around at the same rate as the Earth does at a much greater distance. And therefore, you'd always keep this straight line, this open line of communication between the Earth and this monitoring satellite, allowing you to detect what was coming off the sun and to report back, because you're not necessarily on the other side of the sun half the time.
Yeah, exactly. And so if you were, and not only, if you just imagine putting a generic satellite there, and it detects a CME, it might not, you might be on the wrong side of the sun, so you might not even see the part you want to see. But some of the traces of the coronal mass ejection, the early signs of it, might be very wispy particles that are directed, and you really have to be in the line of it to actually be able to pick up there's a sign of a CME about to come, a coronal mass ejection about to come. So you'd have this monitor. It actually looked kind of cool because if you looked at the sun and this thing was big enough, it'd be like a constant blemish. It would always be in the same position on the disk of the sun. If it was, I doubt it'd ever be big enough to see that, but with a solar telescope, maybe you could detect it. So this idea kind of has been, it's just kind of a small little tweak, I guess, but it is interesting then, it gets you thinking about techno-signatures. If we are interested, by the way, this thing would only give you like a 10-minute warning probably in advance. It's not going to be like days in advance because it takes about 8 minutes for light to travel. And then these things travel so fast, they hit us within about sort of half an hour or an hour time scale from leaving the sun. They travel really quick. So it doesn't take too long for these things to smash into the Earth. But you'd get a bit of a warning, maybe up to an hour or something to be prepared. And if we're interested in doing that, maybe, as we often speculate in SETI, the search for extraterrestrial intelligence, maybe other civilizations might be interested in doing that. And so, I wrote a short paper where I just sort of suggested this is something we could look for because it would look so weird. One of the standard things we do when we detect an exoplanet is we can calculate its seven major axis and its period, and we know how heavy the star is, and you can make sure everything lines up. But this would create like an anomalously long transit duration, for instance. So it's moving so slowly that it just takes way too long to go across the star. And so you'd be like, what the hell's going on with this? If it was a statite, it'd be undetectable, by the way. If it was a statite, you can't see it at all because it's not moving. So there's nothing to look for. But if it was a quasite, it would slowly go across the star. And you'd be like, this doesn't make any sense. The transit duration is way, way too long for how long it is. My daughter's just come in.
It's all right. Hello.
Dad.
Are you dressed up as a fireman? Yeah. Okay, let me just try and persuade her to head out. Okay, hold on. I'll give you a bit of tape.
It's all right, we'll finish in
Just want
5
some
minutes.
tape.
Anyway. Kept you long enough.
Okay. All right, there you go. Okay.
Oh, she's very sweet. How many have you got now?
What? Two. Sorry, I don't know why I always had to think about that.
It's just like
I was just thinking about the BBC.
I was
clip.
as well. You put her on your knee and just kept going. It'd be fine. Yeah. I was expecting your wife to come in and just like she just drags off.
Yeah. No, she would help out.
Scandals happen all the time. The question is, how do democracies respond to those scandals?
And what will it mean for the wider region? I think one of your children has just walked in. I mean, shifting sands in the region. Do you think relations with the North may change?
I would be surprised if they do. Pardon me.
That's all right, carry on.
My apologies.
What's this going to mean for the region?
My apologies. South Korea's policy.
Yes, so it would very slowly move across the star. You'd have this really long transit, and essentially, I guess, it looks like they've hacked Kepler's laws to you. It doesn't make sense. The physics of this thing. How is it moving so slowly across the sun, given how far we know it is from its star? It just wouldn't make sense. So it must be something. There's something obviously anomalous going on, and that could be a technological signature. And as you say, because these things have potential benefits in terms of solar monitoring, it could be another civilization attempting to do something like that. So it would make it a system of great interest. Yeah,
and it's easy to look for. We don't need to build a new telescope for this. We don't need to do anything special. The data's already there. We just need to ask, are there any known signals which are moving anomalously slow? And that would be a pretty simple thing that again, these are sorts of projects that I would love to be able to
fund
and look for in these data sets.
It seems strange that nobody's done that yet. It seems like so thinking about the calculation, so you would like time against radius calculation for the planets, for the exoplanets, and then seeing if they fit on the Kepler's law curve.
Right. So essentially what you'd have a period, because this thing repeats.
Yeah.
So its orbital period.
Yeah.
The mass of the star, since you can typically estimate the mass of the stars quite effectively from the spectrum of the star.
Yeah.
And so you'd be able to calculate how fast it should be moving if it was on a circular orbit, and thus how fast its transit duration should be, assuming it was on a circular orbit. Yeah. And then you'd compare that to what you see. Yeah. And this thing would be moving way, way slower, so it'd have an enormously long duration. And so your first thought might be maybe it's on an eccentric orbit, and it's just hanging out at, we're just happening to catch it at apastron, the point of furthest approach. But there's only so eccentric you can make the orbit, because if you make it too eccentric, the thing will collide with the star eventually, because the star has a physical dimension, so it'll eventually go inside the star. So you'd be able to see that it was an impossible eccentricity, and thus this thing shouldn't exist naturally. So there's something very strange about this object.
So you can imagine you could plot the distribution and look for these really extreme outliers that are above that eccentricity limit, and try and find these things if they exist. It seems like naively to me that seems like an easy thing to do, but I'm guessing there's a hell of a lot of data that needs to be crunched. It's a lot
of data, but it's a very straightforward process. I mean, like many things, people don't realize in astronomy that there's not very many of us. There's only something like, I think it's been estimated, it's about 10,000 professional astronomers on Earth, right? So, and only maybe 1,000 of us work on exoplanets, something like that. So there's just not a lot of human beings to do all of the projects. Yeah. And most of the projects people are doing are things that are directly funded through some organization that you've written a proposal to say, I want to look for this type of exoplanet or something. And then you get funding for a PhD to do that, or for a postdoc or something. But if I write a proposal to say, I want to look for quasites, like most of the time, no one's going to take that too seriously, to be honest. They're going to be like, no, we could do, an exoplanet atmosphere survey. And don't get me wrong, that's very worthwhile to do. But if we always think that way, we're never going to be able to do this, the super top, ambitious, lofty science, because it's always going to be perceived as too high risk. But it's very high risk, but it's ridiculously high gain, of course. So there's that toss-up. And that kind of very high risk, high gain science is traditionally very difficult to fund, despite what you often see in the boilerplate labels of these proposal guidelines that, we want to encourage high risk, high gain science. In my experience, it's actually very difficult. I mean, we've seen this with SETI in the US. It's been almost completely unfunded since its inception with Project Ozma, Frank Drake, in the 1960s. So most of the funding has been private, of people who think it's actually worthwhile to do. So especially when it comes to aliens and looking for technosignatures, it's very difficult to get any kind of government funding, especially for that kind of work, because they have to justify the expenses to the public, and maybe some parts of the public think it's not an effective use of financial resources to be doing that. But if we never do it, we'll never know. So there's a trade-off.
I think that's a really nice place to finish. If these are things that you find fascinating, if you're interested in those, head over to the Cool Worlds website. Maybe think about dropping a few dollars to help do some of the research into these topics, and hopefully sometime in the future make them a reality, or at least rule them out. So Dave, thank you so much for going through those things with me and with us. Really, really fascinating, really, really interesting.
A pleasure.
I'll put all of your links down below, so hopefully we'll get some people going over there, and hopefully we can chat again soon to see how that's going, and when there's something else that crops up in the astronomical sphere. Thanks so much.
I'll be ready.
Awesome.
Yeah, thanks.